ECE3400 Project 2, and we are Sanjana and
Michael.
the goal of this project is to gain an understanding on how the amplifier gain is related to device parameters for fundamental MOSFET circuits. In case of common source amplifiers with ideal current source bias in subthreshold region, the gain was found to be minus kappa over sigma. While in the above threshold region, the gain was found to be k times overdrive voltage square over 2 kappa. Also, in the subthreshold region, the gain does not depend upon the bias current in subthreshold region. In case of common source amplifiers with PFET current source, the gain was found to be minus kappa over sigma n plus sigma p. So since sigma n plus sigma p is greater than sigma n, the gain decreases when we use PFET current source. In order to achieve higher gain, we either increase kappa or decrease sigma. In order to decrease sigma, we need to shorten source drain distance and deepen drain junction. In order to increase kappa, we need to maximize gate area. Another way to achieve higher gain is to use a cascode. This is the schematic of the common source amplifier used in the multi-sim simulation. Uh, the above transistor is the PFET, while the lower one is the NFET. Results. The experimental and the simulation results are very close, but we can see a slight asymmetry in case of experimental results. The gain found from the simulation data was found to be minus 10,810, and the gain with measured data was minus 989. The gain with theoretical or calculated gain was minus 384.
This is the differential pair schematic. We can see the bias transistor on the bottom and the two inputs on the sides. We have the two currents I1 and I2, and they combine to form IB or IREF. Since IB, the bias current is subthreshold, and I1 plus I2 is equal to IB, I1 and I2 must be equal to or less than IB. So all the MOSFETs are in subthreshold if the biased transistor is in subthreshold. The minimum drain to source voltage required to keep the current source in subthreshold is equal to VDS, which is supposed to be between 4UT and VT. These are the derivation of the currents for the differential pair. Here's the experimental and simulation results. We can see that the bias current was slightly greater in the simulation at 10 nanoamps and was around 8 nanoamps in the experiment. Here are the curve fits. You can see that they're pretty much the same. The offset, there's an offset added to the experimental data. Here's the exponential graph of I1 and I2 curves. They show the tightness of the curve fits. Here's the transconductance amplifier. We can see the differential pair on the bottom and the current mirror on the top. And we can see that the output is I1 minus I2. Here's the results for the transconductance amplifier. We can see the IV curves for both the simulation and experimental data. For the experimental, the data starts to veer off from the theoretical curve. This is due to the mismatch between the current mirror and the differential amplifier due to variances in the early voltage between the transistors. This is our voltage gain, simulation and experimental. The experimental was a lot lower gain than the simulation was, and it might have been because of our values for the EKV model. We used a VTO of 0.5, a kappa, or a K rather, of 5 times 10 to the negative 5, gamma of 1, and phi of 0.7. Here's our output resistance. We saw that the output resistance on the simulation was much greater than the output in the experimental. Here's our transconductance graphs, and we found that the transconductance of the simulation was much less than the experimental data. Thank you for watching. All right.